Professor Won. Hello everyone, I'm Shogo Kawahara from MIRISE Technologies Corporation. Today I'd like to talk about a high accuracy resistance measurement system. Here is outline. Let's start with the introduction. The current sensors are widely used in battery management system of electric vehicle. The current sensor measures the battery load current. It's integrated to calculate the input and output total charge from the battery for state of charge estimation. In this application, the current sensor is required to be low offset and low gain error. The shunt-based current sensor is often used as the high accuracy current sensor in BMS. The battery current is converted to the voltage across the shunt resistor. The resistance is very small, about 25 microohm to measure 2000 ampere battery current. Our target gain error is less than 0.5%. Here is the breakdown of the gain error. The shunt resistor long-term drift is the main cause. So we need to calibrate and measure the shunt resistor long-term drift. And next, let me review two prior art of the long-term drift calibration method. One prior art uses high pressure reference current to measure and calibrate the long-term drift of shunt resistor. The shunt resistance is calculated by the voltage across the shunt resistor divided by non-initial value reference current. In this method, the accuracy relies on the reference current. It has a long-term drift, and which causes shunt resistance measurement error. The other prior art uses long-term reliable reference resistor and with ratiometric resistance measurement technique. The current generator applies the excitation current to reference resistor and shunt resistor. The shunt resistance calculated by the ratio of the voltage across these resistors multiplied by non-reference resistance. The advantage of this method is that the FE measure synchronously them. The noise and current or noise and drift of the reference current, excitation current is rejected. So therefore, a long-term drift of the reference current doesn't affect the measured shunt resistor. The disadvantage is that the reference resistor long-term reliability is commercially available only 10 or more. These resistance ratio between these is 400,000 to 1. So the required dynamic range of FE is more than 175 dB. That's impractical. So our proposed system solves this disadvantage. Next, let me explain the concept of the proposed system. To relax the required dynamic range of FE, we add the general purpose 10 million reference resistor 2 between the reference resistor 1, the shunt resistor, and we measure the shunt resistor in two steps. In step 1, the resistance ratio of reference resistor 1, 2 is obtained. In step 2, the reference resistor ratio, reference resistor 2 and the shunt resistor is obtained. And as in the prior art, the synchronous measurement reject the noise and drift of the reference current. So the shunt resistor calculated by these results multiplying by non-reference resistance. So therefore, the required dynamic range is required relaxed to more than 126 dB. But however, in step 2, large excitation current about 1 ampere is required to achieve this high SNR. with these low resistances. So if we consist this current generator of the linear regulator, as in the prior one, it consumes high power. So to efficiently generate test current, excitation current, we use the switching regulator-based current generator. And to avoid the 1/f noise of FE, we measure a low frequency resistance ratio of these, and with locking technique. This slide shows a block diagram of proposed system. There are two FEs in ASIC, followed by DSP, to measure resistance ratio. These FEs synchronously measure the resistance voltage to reject the current, noise, and drift, as I mentioned. Next, let me explain the circuit operation for shunt resistance measurement. In step 1, DC test current 4.5 milliampere generated by linear regulator-based current generator applied to this resistor, and the resistance ratio is measured by FE and DSP, and now with the Sync 3 and integration filter. In step 2, the test current 1 ampere 162 Hz generated by switching regulator-based current generator, and the low frequency AC resistance ratio is measured by FE and DSP with locking technique. Next, let me explain the detail of switching regulator-based current generator. This slide shows the detailed circuit configuration and timing diagram. The switching regulator current generator based current generator consists of two blocks: the charge sampling stage and the switching regulator stage. The charge sampling stage supplies the intensive rush current from VDD to the load, and the switching regulator stage operates at the switching signal 15 kHz, and it's modulated at 162 Hz. And modulated switching signal allow us to use small surface-mounted inductor and capacitor. Here is the system prototype photograph and chip micrograph. Our proposed system consists of shunt resistor, reference resistor, current generator, ASIC, and FPGA. The DSP is implemented in the FPGA and MATLAB. The prototype chip was fabricated by 180 nanometer BCD process. The active area is 4.49 square millimeter. Next, let me show you the measurement results. Here is the measurement input referred spectrum density of the FE1 and FE2 in step 2. And measuring the 10 ohm and 25 micro-ohm with this signal. And we can clearly see the measurement signal at 162 Hz, and the thermal noise density of FE is the 150 nanovolt over root Hz. And the flicker corner frequency below the 10 Hz. And the signal of FE2 is smaller than FE1, and so the SNR of FE2 dominates the SNR of each step. The SNR of step 1 is 70 dB, and step 2 is 65 dB with this filter effective noise bandwidth of 8.33 MHz. The system SNR calculated by this result is 64 dB. The expected shunt resistance measurement error is 0.19%. Next, let me show you the measurement shunt resistance error. Here is the histogram of the shunt resistance measurement error with this condition. The measured 3 sigma error is 30 nano-ohm or less with 25 micro-ohm shunt resistor. It consists of the estimated error calculated from system SNR, as I mentioned. This shows the switching regulator-based current generator output current and current gain as a function of input current. When output current is 1 ampere, the input current is 42 milliampere, the current gain is 23.3. The switching regulator-based current generator reduces the power consumption by 1/23 to linear regulator. This table summarizes the performance of the proposed resistance measurement system with the prior state-of-art systems for current sensors. The proposed system achieved the higher power efficiency and the lower resistance measurement error. Finally, I'll summarize my presentation. This work proposed high accuracy and low power shunt resistor measurement system with two-step ratiometric resistance measurement technique and AC excitation with switching regulator-based current generator. The proposed system prototype achieves shunt resistor measurement error 30 nanohm or less with 4.5 milliampere and 1 ampere RMS. The current generator achieves a superior low power. Thank you for your attention.